Einstein in 1905, among a whole bunch of other things, said that light exists as a particle. So it's not just a wave now. It's not just a wave with this electric field wave going with this magnetic field wave perpendicular to each other and traveling perpendicular to both of those. Now we're recognizing that light has a particle nature associated with it as well. And Einstein called that particle nature of light photon theory. Light exists as a photon or a quantum of energy, a particle of light. This photon, this quantum of energy, or this particle of light, has an energy associated with it. The energy of that photon is equal to h times f, or we could say that it's equal to hc over lambda. So you can see right now the connection between particles and waves. Einstein's saying that it's a particle, but the energy of this particle is related to its frequency and its wavelength, which of course are both wave properties. So the particle-wave duality here now, or the wave-particle duality as we usually call it here. What's this H thing? What do we call that? That's the only term in there that isn't really familiar to us since even Physics 20. Daxon, what's the H? It's called Planck's constant. It's actually named after the guy who introduced the idea of quantum theory, not photon theory, but quantum theory, and that's the idea that energy has to be quantized. In other words, energy can exist as this amount or this amount or this amount, but not anything in between. And then Einstein built on Planck's quantum theory to extend that idea to particles of light, photons of light. The value of Planck's constant can be one of two values, 6.63 times 10 to the minus 34 joules seconds, or it can be 4.14 times 10 to the negative 15 electron volt seconds. Which one do we end up usually using? We're going to usually use the first one. And in fact, we can always use the first one if we want. If in the end we've got a number given to us in electron volts and we still want to use that first one, what do we have to do? We just have to convert that electron volts to joules. The big thing is here, you've got to be consistent. If you're doing electron volts, then stick with the electron volts through this whole question. If you're dealing with joules, then stick with joules through the whole question. If in doubt about when you can use it and when you can't, this second value that is, then just use the first value because it always works for us. As I said before, it just ends up being a little bit of extra work sometimes, but it always works. Okay, if you're allowed to use the second equation, and so far, in all the questions we've done so far, you have been allowed to use the second equation, then go ahead and do it if it's convenient. If it's not convenient, then don't bother doing it. Okay, we're going to learn a couple of situations today where you're not allowed to use that second constant, the 4.14, where you have to use the 6.63. And after today, some of you probably will look at it and say, you know what, I think I'd just rather use the 6.63 always, because it's a little bit confusing when I'm allowed to use it and when I'm not allowed to use it. Okay, whatever ends up working for you after we're done today. All right. We've done a number of problems on photon theory here over the last few days. I don't think there was any issues with that stuff, was there? Okay, the E is equal to h times f. Sometimes we had to find a number of photons. Sometimes we had to find a, total energy or energy for one photon divided and so on. They were good with that stuff? All right, on Friday we started talking about the photoelectric effect, which is a phenomenon that was discovered in 1897 by Heinrich Hertz, and essentially it boils down to this. When EMR of any type for that matter, but specifically visible light, because that's the kind that we can see, strikes a piece of metal, other things as well, but usually metals, because electrons leave metals easier, sometimes an electron is ejected. Sometimes electrons leave. And if we can harness that, then essentially we can turn it into an electric current. So it's the generation, essentially, of an electric current by light. Light strikes the metal, electrons leave, we've got an electric current. Here's the thing, though. It was discovered in 1887 by Heinrich Hertz. Hertz tried to explain what was happening, but he couldn't. Nor could anyone else explain what was happening until 1905, when Einstein comes along. Einstein said in 1905 that the reason that electrons were sometimes not being ejected was not because we didn't have enough light. That's what Hertz said, right? The electrons not being ejected, let's just get more light. You got a flashlight shining on this metal, no electrons being ejected, get a brighter flashlight. But that didn't work. In order to get electrons ejected when we didn't have them ejected before, we don't need to change the amount of light, we need to change the type of light. And if we use Einstein's theory or go back to Einstein's photon theory, that makes perfect sense. If we need more energy to cause an electron to be ejected, we don't need more light. If we need more energy to cause an electron to be ejected, right, we need more energy, we need a higher frequency of light. In other words, we need a different kind. Tell me this, please, answer this question. If red light is not causing an electron to be ejected, tell me something that I might try that might cause an electron to be ejected. Violet light. Okay, there's no guarantees of that, but violet light has a chance because it's higher than the frequency of visible light. Even if you have really, really bright red light and really, really dim violet light, the violet light has a better chance of causing electrons to be ejected because it has a higher frequency, and therefore it has a higher energy associated with it. What happens, though? Let's say violet light is above that threshold frequency, that minimum frequency that we talked about on Friday that's required for an electron to be ejected, that F0, a threshold frequency. Let's say violet light is above that value. Let's say you have a single photon of violet light. How many electrons are you going to get ejected? One. Yeah, it's going to be one. Let's say you have 1,000,000 photons of violet light, and violet is above the threshold frequency. Then how many photons are you going to get ejected? Sorry? What did I say? Photons, sorry. Yeah, you're right. How many electrons are going to be ejected? 1,000,000. If you're above the let's say you're below the threshold frequency. Red is below the threshold frequency. One photon produces 0 electrons. 1,000,000 photons produces 0 electrons. If you're below the threshold frequency, the minimum frequency of EMR necessary to eject an electron, it doesn't matter how much you got. It doesn't matter how bright the light is, how many photons you have, nothing happens. Let's say, though, you're above the threshold frequency. You're at that violet light. One photon will cause 1 electron. 1,000,000 photons will cause 1,000,000 electrons to be ejected. Let's say now, though, that you're way above the threshold frequency. Let's say you don't have violet light. Violet light's above the threshold. But let's say now you get X-rays. One photon will do what? No. One photon will still only cause 1 electron. It's a one-to-one thing. If you're above the threshold frequency, it doesn't matter how high above, one photon will still just cause 1 electron to be ejected. So what's the difference now? That electron will be more what? More vigorous, did you say? Okay, that's a different way to say it, but sure, that works. It's more energetic, right? It's more energetic. It's moving faster. So why is it moving faster? Well, look, an X-ray is way above the threshold frequency. Therefore, it's got a lot of extra energy that it doesn't really need. Okay, you're already above the minimum energy, the energy necessary to eject the electron. So now you got a whole bunch of extra energy. Where does it go? Well, it goes to the electron. It just makes the energy of the electron higher. It makes the electron go faster. So one photon that's way above the threshold frequency, maybe it's in the range of X-rays, it causes 1 electron, but a more energetic electron. 1,000,000 photons above the threshold frequency or way above the threshold frequency will still cause 1,000,000 electrons, but they're going to be 1,000,000 really energetic electrons. Jackie? Threshold frequency is the minimum frequency of EMR necessary to eject an electron. That's a good question. Do we know what that is? Well, for each different material, it's a different value. So the threshold frequency for, say, cesium would be one value. I don't know what it is. The threshold frequency for aluminum would be a completely different value. Each different metal has a unique threshold frequency. So some of them are better at ejecting electrons than others. Okay, some of them require ultraviolet light to cause the electrons to be ejected, and some of them would only require visible light, or conceivably even less, to cause the electrons to be ejected. Yeah, either you're going to have to be given the threshold frequency, or you'll have to be finding the threshold frequency given other things, yes. Sometimes they may express it not in so many words, though. Sometimes you got to read between the lines. They might say, Jackie, they might say, light of frequency blah, blah, blah is required to eject electrons. Well, they're telling you that if this frequency is required to eject electrons, well, then that's the threshold frequency, right? That's the minimum frequency. So they might not use the word threshold frequency, but they'll have to give you threshold frequency, or, again, ask you to solve for threshold frequency given other things. The work function we defined on Friday as the minimum energy necessary to eject the electron. And of course, if the minimum frequency is F0, and the energy is E is equal to h times F, then the minimum energy would be h times the minimum frequency, h times F0. Well, we also said, by the way, that E is equal to hf or hc over lambda. If we extend that to the work function equation, this part of the equation we didn't write down on Friday, it would be hc over lambda. What would we say, lambda? Yeah, the threshold wavelength, yes, but it's not a minimum wavelength. It would be a maximum wavelength, right? Because frequency and wavelength are inversely related to each other. So if you're talking about a minimum frequency, extend that to a wavelength, you got to be talking about a maximum wavelength. Anything below a certain frequency won't cause the electrons to be ejected. Anything above a certain wavelength, the threshold wavelength, won't cause the electrons to be ejected. Does that make sense? John, question? Okay. Good. So if we say that red light won't cause the electrons to be ejected, violet light will, we could say that, we could express the reason for that in a couple of different ways. We could say that it's below the threshold frequency, and red light, that is below the threshold frequency, and therefore won't cause the electrons to be ejected. Or we could say that it's above the threshold wavelength, and therefore won't cause the electrons to be ejected. Red light has a smaller frequency than violet. It has a larger wavelength than violet. It's below the threshold frequency. It's above the threshold wavelength. So any way you look at it, it's not going to cause the electrons to be ejected. Okay, this is where we left off on Friday. We didn't write this down, but we did talk about this on Friday, and we talked about it in our review here today. When you're below the threshold frequency, nothing happens. It doesn't matter how many you have. When you're above the threshold frequency, the electrons will be ejected. And it's a 1-to-1 ratio. One photon above the threshold frequency causes one electron. But when you're way above the threshold frequency, or you got a higher frequency than is even necessary to cause the electrons to be ejected, then it's going to cause those electrons to be ejected still as a 1-to-1 correspondence, but each one of them is going to be more energetic than when we use the frequency that's just barely above the threshold frequency. Couple of more terms to define here now. One's called the stopping potential. Now, we're going to define this, but as we do that, it might not make a lot of sense as to why we would want to even do this. Okay, that will come in time. Okay, I promise you. Just trust me for now. The whole idea of stopping potential and its usefulness will come a little bit later today. The stopping potential is defined as the potential difference required to stop an electron that has already been ejected. So an electron is ejected, an electron leaves, so therefore the light must be above the threshold frequency. If we apply a potential difference, then we can either cause that electron to speed up, or we can cause it to slow down. If we apply a big enough potential difference, we can actually cause the electron to stop. So basically, it just kind of floats. It's left the metal, it's gone. Now it's just moving through the air, but we've applied a potential difference to slow it down and stop. Okay, again, why would we want to do that? Well, ultimately, you're going to learn a little bit more about that later today, but it boils down to this. Hey, maybe you want to do an experiment to find the threshold frequency of a particular metal. Okay, that's a useful thing to do. Okay, potentially, stopping the electron is a useful thing to do in order to find the threshold frequency. Again, we'll see that a little bit later today. Okay, for now, kind of just trust me on it. The definition of it, by the way, the symbol for it is V stop. And it is the potential difference required to stop an already ejected electron, an electron that's already left the metal. Yeah. Now we're going to introduce our second equation that applies to the photoelectric effect here. The first one, remember, actually the third one. The first one you might remember, E is equal to HF is equal to HC over lambda. That's not unique to the photoelectric effect. That's valid anytime we have a photon, but certainly we're dealing with photons in the photoelectric effect, so it's still valid. We also have that next equation that we learned on Friday. The work function is equal to H times the minimum frequency, or the threshold frequency. And it's also equal to HC over lambda max, the maximum wavelength. Now a new equation that relates to this whole stopping potential, we're going to say the maximum kinetic energy of an ejected electron, we're going to call it EK max, is equal to, well, of course it's going to be 1/2 mv max squared. That's not a new equation. But the maximum kinetic energy will also be equal to Q times V stop, the stopping potential. Now, if you take a step back from this, that equation doesn't seem new to us either. In the end, what we're saying here is 1/2 mv squared equals QV stop. Kinetic energy is converted to potential energy. And if we want to find the stopping voltage, or the stopping potential, then we can say that 1/2 mv squared equals QV stop, or we can simply say that EK is equal to QV stop. So far, all of these equations in one form or another appear on our data sheet. Lastly, though, before we start solving some problems, we have to look at the law of conservation of energy in the context of the photoelectric effect. The law of conservation of energy says EI equals EF, right? The total initial energy equals the total final energy. What initial energy do we have here? What is it that possesses the energy before the electron is ejected? The photon. So let's say that our initial energy is going to be equal to H times F. What is it that has the energy after the electron has been ejected? The electron. What kind of energy is that? It's kinetic energy. But the kinetic energy that we have in the electron is less than the photon energy that we started off with. Why? Why would it be? Why would the energy that we end up with in the electron be less than the energy of the photon that we started with? Some of it was used up in the process of ejecting the electron. Anybody want to take a stab at how much was used up in ejecting the electron? Small amount. Depends. How about the minimum energy necessary to eject the electron? So what we start off with is H times F, the photon energy. What we end up with is the kinetic energy of the electron. But of course, if the kinetic energy of the electron is less than the energy of the photon that we start with, then we've got to add together the energy that we end up with plus the energy that we used up in the process of ejecting the electron. The electron needed to absorb a certain amount of energy to leave, and then once it leaves, it's got kinetic energy. The work function is the energy that is absorbed in order to be ejected. Yeah, Annie? Absolutely. In fact, this equation becomes very versatile. Unfortunately, it doesn't actually appear on our data sheet. But it becomes very versatile. A lot of times we're going to end up replacing HF with HC over lambda, as you just suggested. A lot of times we're going to end up replacing EK max with QV stop or with 1/2 mv squared. A lot of times we're going to end up replacing W with HF0 or HC over lambda max. So a lot of times you're going to use this equation, but it's not even going to look remotely close to the way that it appears on the board there right now. You're going to replace all three things, all three expressions with other equations. Sometimes you won't. Sometimes you will. It's a very versatile equation. In fact, it's probably the most common one that you're going to use in a photoelectric effect problem, although you'll often use it in conjunction with others. The downside to it is it doesn't appear on our data sheet for whatever reason. I think maybe the reason it doesn't appear is because ultimately they want us to be able to derive it, I think, from the law of conservation of energy. It's not that hard though, right? The energy that we start with is equal to the energy that we end with plus whatever we used up in the process. Excellent question. Yes. It's under conservation of energy, yes. All right, let's take a look at our first sample problem for the day, our first of 3 sample problems for the day. Blue light shines on a metal surface shown in figure 14.13. I don't even care about the diagram. It causes electrons to be ejected. The photo emission of electrons, the ejection of electrons. If a stopping potential of 2.6 volts is required to completely prevent electrons from reaching the collector, in other words, this potential difference is required to stop the electrons. And we want to determine the maximum kinetic energy of the electrons. We want to express the answer in both joules and electron volts. Let's write down some givens here. What is this 2.6 volts thing? Annie? Yeah, we're going to call that V stop. Okay, we're not told specifically that it's the stopping potential, but if we read between the lines, we in essence are told that. 2.6 volts is required to completely prevent electrons from reaching the collector. In other words, it's required to stop the electrons. That's the definition of stopping potential. We want to determine the max kinetic energy of these ejected electrons. Let's go back to the equations that we learned are valid for the photoelectric effect and see if we can find one that will work here. Which of these equations do you see on this board do you think you're going to try to find the maximum kinetic energy with? Right? Yeah, let's try that one. EK max is equal to QV stop. Do we know what Q is? What is it, Paige? Good. 1.6 times 10 to the minus 19. Now, we're going to drop the negative sign in front of the 1.6 because we always do when we plug the charge of an electron into an equation. But it is just the charge of an electron. How did she know that it was the charge of an electron here? What is it that's being ejected? An electron, right? Good. So we're going to make it 1.6 times 10 to the minus 19, even though it's really negative 1.6. The stopping potential is 2.6 volts. In this question, as long as you recognize, what your variables are and what to plug into what, it's a pretty easy question, right? What does it work out to be there? 4.16 times 10 to the minus 19. What units would that be? The standard units are joules, and as long as we're going with the standard units throughout the question, of course, we're going to get joules. We're going to round that actually to 2 digits, though. 4.2 times 10 to the minus 19 joules. Then we're going to convert it to electron volts. We're going to say 1 electron volt over 1.6 times 10 to the minus 19 joules equals X electron volts over 4.16 times 10 to the minus 19 joules. Now, I'm going to do some lightning fast math in my head, and I'm going to say that the number of electron volts is 2.6. Is that right? Oh, is that ever quick or what? A lot of people ask me this question, is it always going to be the same as the number of volts? If you're dealing with an electron, yes. Yes, it will. If you're dealing with an electron, yes, it will. Why? Because we define electron volt as the energy in joules gained by an electron as it goes through a potential difference of 1 volt. Okay? All right, let's take a look at these 3 questions that go along with that practice problem, please. All right, if we have no issues with this question, let's take a look at our next sample problem. It says 14.5 on 718 says, experiments show that the work function for cesium metal is 2.1 electron volts. What's the threshold frequency and the threshold wavelength for photons capable of producing photoemission from cesium? When we're looking for the threshold frequency, we're really looking for the minimum frequency. When we're looking for the threshold wavelength, we're really looking for the maximum wavelength. So let's go about solving this now. We've got a work function of 2.10 electron volts. We've got that we're looking for the threshold frequency, and we're looking for the maximum wavelength. Now, of course, it stands to reason the equation we're going to use to find the threshold frequency is going to be W is equal to H times the threshold frequency. Now, what value of Planck's constant do we use? We're probably going to use the 4.14 value because it has electron volts in it, right? If we want to use the 6.63 value, can we? Sure we can. But if we do that, what do we got to do first? We've got to convert it to joules, right? The 2.1 electron volts to joules. We can do that. That's fine. But in this case, we're allowed to use electron volts. So you want to save yourself a little bit of work. Let's go ahead and do that. Work function of 2.10 electron volts over Planck's constant of 4.14 times 10 to the negative 15 electron volt seconds. What do we get when we divide those two? 5.07 times 10 to the 14. Okay, that makes sense, probably visible light, right? 5.07 times 10 to the 14 hertz. Now, if we want to find the wavelength, let's use the other equation. W is equal to hc over lambda max. Rearrange that. Lambda max equals hc over w. Once again, we're going to use that value 4.14 times 10 to the negative 15 times 3 times 10 to the 8 divided by the work function, which is 2.10. By the way, does anybody see another way that we could have solved for the lambda max after we solved for threshold frequency? Yeah. You could have, yeah, you could have, for sure. But you also could have just said V is equal to F lambda. V is 3 times 10 to the 8. My threshold frequency is 5.07. My maximum wavelength would be lambda in that equation. That requires you to already have the threshold frequency, though. If we're doing this from scratch, we solve for lambda max first. We got to do it this way. Lambda max is equal to hc over w. What do we get for that, by the way? 5.91 times 10 to the negative 7 meters. Okay, good. Now, pretty soon we're going to encounter problems where we can't use that 4.14 electron volt value for Planck's constant. I'm going to tell you right now when we can and when we can't use it, so that when we encounter that problem where we can't use it, you know that you can't use it. Here's a rule of thumb. You can use it whenever it's convenient to use it, except when you're using the equation 1fmv squared or qv stop. If you're using one of those two equations, you cannot use electron volts. You must use joules. So if you're using one of those equations in conjunction with something else that needs Planck's constant, you've got to use the 6.63 value. Does that make sense? If that confuses you, just always use the 6.63 value. It just means a little bit of extra work. All right, let's take a look at a couple more problems that go along with that. 718, see what you can do with those over the next 5 minutes, and then we'll check them over if we need to. Let's take a look at both of these questions here, everyone, please. Number 1 says light of 480 nanometers is just able to produce photoelectrons. A photoelectron, by the way, is an electron that has been ejected. So it's an electron that's gone. It's left the metal. It's an ejected electron. When striking a metal surface, what's the work function of the metal? So in question number 1, we're going to say that the threshold wavelength, or the max wavelength, is 480 nanometers, which we're going to convert to meters by multiplying it by 10 to the minus 9. We're looking for the work function. We're just going to say for question number 1, W is equal to hc over lambda max. Now, we can kind of cheat a little bit and look at our answer and say, oh, they're looking for the answer in electron volts. So probably what value of Planck's constant do I want to use? 4.14. Now, if in the event that I use 6.63, that's okay. But if I'm looking for an answer in electron volts and I use 6.63, what do I got to do? Going to get an answer in joules, then I got to convert it to electron volts, right? Let's just use the 4.14 value here. It's 4.14 times 10 to the negative 15 times 3 times 10 to the 8, divided by lambda max, which is 480 times 10 to the minus 9. And I assume when we do the math on that, it works out to be 2.59 electron volts. Is that right? Is that right? Daxon, what was the problem with that one? Oh, instead of 4.14. Okay. Just make sure you check that data sheet frequently, just so that you don't get in the habit of putting the wrong number in, right? It's easy to, to just misremember, if that's a word. George Bush says it's a word, anyways, I think. I think he misremembered. He misremembered. It's easy to not remember correctly a constant, so that's why it's on our data sheet, in case we don't remember it correctly. Okay, let's look at question number 2, which is, I think, a tougher question. It says blue light of wavelength 410 nanometers strikes a metal surface for which the work function is 2.1 electron volts. We're going to say the wavelength here is 410 nanometers, or 410 times 10 to the minus 9 meters. That's not the threshold wavelength, because it doesn't tell me or even infer that it's the maximum wavelength possible. Just here's the wavelength of the light. It tells me the work function is 2.1 electron volts. We're looking for the energy of the emitted electron. What kind of energy does the electron have once it's emitted? Kinetic. So we're looking for EK, in fact, EK max. Let's go back to that page where I had all my equations on, remembering that we have lambda, W, and we're looking for EK max. And see which equation you think you're going to use to solve for that. What do I have? Lambda, W, EK max. What do you want to do here? Spencer? Let's use HF is equal to EK max plus W, the one that doesn't appear on my data sheet. Now, we got a bit of a problem here, but it's not a big one. I don't know what F is, right? But somebody asked me, I think it was Annie. No? Somebody else asked me then, can I just replace HF with HC over lambda? Of course I can. E is equal to HF, that equals HC over lambda. So let's just switch this equation to make it HC over lambda is equal to EK max plus W. Now I'm looking for EK max. Let's plug our numbers in here. We allowed to use 4.14 for this? Yes, we are. We're not allowed to use 4.14 when we've got 1/2 mv squared or QV stop in there. EK max can be in electron volts, I just can't use electron volts if I'm setting EK max equal to 1 half mv squared or QV stop. I'm not in this question. So it's still okay to go with electron volts. 4.14 times 10 to the minus 15 times 3 times 10 to the 8 divided by 410 times 10 to the minus 9. By the way, would it have been okay if I had have gone with 6.63? Sure it would. What would I have had to do, though, if I went with 6.63? I would have had to convert 2.1 electron volts to joules. This just saves me a tiny bit of work, that's all. Let's do this one as a class here, okay? Let's say 4.14 times 10 to the minus 15 times 3 times 10 to the 8. Let's get a number on the top there. Let's divide it by 410 times 10 to the minus 9. 3.02926. Let's bring the 2.10 over to the left-hand side by subtracting. I get 0.929. What would the units be? It would be in electron volts, right? If you solve for the frequency, you should, yeah, because no, it should make a difference, because if you solve for the frequency, how are you doing that? Well, frequency is C over lambda. So all you're doing is replacing, all you're doing is kind of separating the equations instead of putting them together like that. It should work out to be the same. Now, whether it's 0.929 or 0.932, I'm not sure, but it should be the same either way you look at it. Spencer, you did it that way and got you did it my way and got 0.929? Oh, you got 0.932. Okay, so let's take a look at what we did wrong here then. What did you use for Planck's constant? 6.63? Okay. 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 So yeah, that's we encounter that every once in a while. We use joules, we get one number. We use electron volts, we get a different number. Should they be the same? Of course they should be the same. Right? They're both valid things to do. Of course they should be the same. Now, why aren't they the same? Because they're rounded numbers. We talked about this a little bit earlier, right? They're rounded numbers. This 4.14 is really 4.14 something, something, something times 10 to the minus 15. And the 6.63 is really 6.63 something, something, something times 10 to the minus 34. So how do you know which one to use then? I get a value of 0.929. I write that down in my numeric response question. You write down 0.932 in numeric response question. Who's going to get the right answer? Yes, both. Okay. When they write these exams, diploma exams, okay, they think of all of these things. They've field tested all of these questions a million times. They know all the different possibilities that are going to happen here, and they know that I did it correctly, and they know that you did it correctly, and therefore both answers will be keyed correct. So you don't have to worry about that, okay? Okay, you don't have to worry about that. We're both correct here. Yeah, I use the electron volts, which I think makes a little bit more sense here because it's quicker. You use joules, though, you shouldn't get the wrong answer by using joules. So we're both right, 0.929 or 0.932. Is that good? All right, let's try another one. Using table 14.1, which I don't actually have 14.1 up here, I guess. Determine the maximum speed of electrons emitted from an aluminum surface if the surface is illuminated with 125 nanometer ultraviolet light. One thing we do know is the wavelength of the light. It's 125 nanometers. Now, and the table gives you the work function. So the work function for aluminum from the table is 4.08 electron volts. We want to determine the max speed of the electrons, of the ejected photoelectrons here. Remember, you see a wavelength, don't automatically assume it's the maximum wavelength, because it's not here, right? It's just saying look, you're shining this light on it. It's not saying this is the maximum wavelength or the minimum frequency, whatever. It's just, here's the light that you're shining on it. Maybe it's well above, maybe it's well below. Let's solve for Vmax here. Any suggestions? You guys should all have the equations all written down in one place in front of you. If not, then check your data sheet. Or look for an equation that's not on your data sheet. Which one do you want to try? HF is equal to EK max plus W. Well, okay, go ahead and try that. If in the end you recognize that you got a photoelectric effect problem and you can't figure out in about 5 seconds which equation to use, then in the end you're probably going to end up using that one. So if you're not sure, go straight to that one, the one that doesn't appear on your data sheet. But my problem with that is I don't know what F is, nor do I even have Vmax in this equation. So what am I going to do? No, I can't find F using W is equal to HFO. I can't find F using W is equal to HFO. So how am I going to find it? Right. You can replace HF with HC over lambda, or, as Kurt did, I think, in the last question, you can say F is equal to C over lambda, get the value for F, and then plug it into there, plug the number into there. It doesn't really matter. Nicole, what was the next thing you said? EK max? Right. So you're going to replace EK max with 1/2 MV max squared. Is that okay? Could you replace it with QV stop? Sure you could. Wouldn't help you because you're looking for Vmax, but you could replace it with QV stop. And we add that to the work function. Now, what do you notice about this problem? It uses 1/2 MV squared. We cannot use electron volts. We can't. We have to use joules in this question. Okay, if you're confused by that at all, again, just always use joules because it always works. I'm sorry? We can't use electron volts because the equation 1/2 MV squared using kilograms in meters per second automatically comes out to be standard units, which are joules. So as soon as we introduce that equation, we've got to use joules. Let's convert this 4.08 electron volts to joules. 1 electron volt over 1.6 times 10 to the minus 19 equals 4.08 over x. What does it end up being? Going to be somewhere around, okay, 6.528. Okay, so let's plug in some numbers now. Let's use the value of Planck's constant that always works. What mass do we use? It's been an electron that's been ejected, right? So let's use the mass of the electron. Now, mathematically, it's a little bit tricky here. Let's go through this on our calculator. Let's say 6.63 times 10 to the minus 34 times 3 times 10 to the 8. Let's get a number on the top there. Divide it by 125 times 10 to the minus 9. It gives us a number on the left-hand side. What do I do next? Take the 9.11 over or the 6.52? 6.52. It's not attached to it, right? So let's take that over first. We're going to take that over by subtracting. So let's take that number on the left-hand side, subtract from that 6.528 times 10 to the negative 19. We get 9.38 times 10 to the negative 19. Let's multiply that by 2. I'm sorry? Is that okay? Okay, then let's divide that by 9.11 times 10 to the minus 31. And then what? Listen, if this is a multiple choice question, one of your options will be 2.06 times 10 to the 12. because a very common mistake is forgetting to square root it. But if you see that, you know it's got to be wrong because it's greater than the speed of light. If you get an answer for a speed that's somewhere in that range of 10 to the 12, 10 to the 13, in all likelihood, you forgot to square root it. So let's square root this. And lo and behold, we get 1.44 times 10 to the 6, which is a pretty reasonable speed for an electron. Let's say 1.44 times 10 to the 6 meters per second. Maybe sometime you got to replace EK max with QV stop. Not in this question, but maybe you do. Maybe sometime you got to replace W with H times F0 or HC over lambda max. Not in this question, but you see that as soon as you introduce this equation here, the one that doesn't appear on our data sheet, which we're going to do often, okay, a lot of times we got to do something else as well. Okay, we got to sub in another equation for some expression that's already in there. All right, I'll give you a second to copy that over if you haven't already, and then we'll move on to the practice problems that go with this one. Let's take a look at these problems now and see how they go. Sorry guys, real quickly, you need that table to answer question number 2. The work function for cesium from that table was 2.10. Yeah, you definitely need that data to solve this question. That'd be given to you on a test, of course, too.